Hello everyone, a very good evening to all. Uh, Myself Vivekananda Naik, I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. I work in the Plasma Physics Laboratory. So I welcome you all once again for this ninth interaction session on atomic and molecular physics, which is being flowed this January 2025 session by NPTEL with course code NOC 25P04. So today we will be discussing a few questions that will be based on the week 9 lectures of atomic and molecular physics course, this course. So if we talk about the topics covered in the week 9th lecture, so basically it was mainly related to the molecular spectra. The molecular spectra portion has already been started, and there was lectures related to rotational spectra of molecules. So if we talk about diatomic molecules, so go through a few. Let's go through a brief discussion about molecular spectroscopy. So so in case of atom, we only had electronic spectra, like that was transition between the electron levels, that was denoted in terms of spectroscopic notations n, then 2s plus 1 lj. So this was the notation. So there were different energy levels, and according to the selection rule, there are transitions, and we are getting spectra, whether it be X-ray spectra or electronic spectra. So all these things we had already covered in atomic spectra portions. Now coming to molecular spectra. So diatom molecule shows basically three types of spectra. So three types of spectra. They are electronic spectra, rotational spectra, and vibrational spectra. Rotational spectra and row vibrational by rotational vibrational spectra. Now, if you talk about the value of energy for electronic spectra, the energy is of the order of 0 to 10 electron volt. Then, for pure vibrational spectra, so for vibrational spectra, energy level is 0.1 eV order. Then, for rotational, it is 10 to the power minus 3 eV order. So, electronic spectra rise in the visible or infrared region, visible and UV region, visible UV region, and vibrational spectra according to their energies, they lie in infrared region, and rotational spectra, they lie in microwave region of electronic spectrum, electromagnetic spectrum. Now, if we talk about how the levels are arranged, so suppose, so this is B, this is A. So these are electronic spectra. Electronic spectra levels. Then corresponding to each electronic spectra, there are a number of vibrational spectra. So there are a number of vibrational spectra. And similarly, corresponding to this B, there are also a number of vibrational spectra. So they are denoted by V, which is 0, 1, 2, 3. Again, this is V prime, 0, 1, 2, 3. Then corresponding to each vibrational level, there are rotational levels. So corresponding to each vibrational level, there are rotational levels like this. In here also, there are rotational levels, and they are denoted by J. So J is equals to 0, 1, 2, 3 like that. So if you talk about the transitions and the spectra coming out of the transitions, so in electronic transition, there is transition from one electronic level to another electronic level, so which give rise to electronic spectra. Then if transition occurs between two vibrational levels, then it is vibrational spectra. And if transition occurs between two rotational levels corresponding to same vibrational level, for example, if the transition occurs between these two, since it has same vibrational level, that is it is called as pure rotational spectra. Pure rotational spectra. Then if you talk about the spectra that come from rotational levels of different vibration levels, then suppose transition occurs from this level to this level, then this is called as rotational vibrational spectra. Rotational vibrational spectra. So these are some of the discussions. Now if you talk about diatomic molecules, there are basically two types of diatomic molecules. One is heteronuclear, or one is homonuclear, and another is heteronuclear. Now homonuclear means the diatomic molecules which doesn't have permanent dipole moment, means their positive and negative charge and their positive and negative center of charge coincide with each other, and they are homonuclear diatomic molecule. For example, H2, N2, O2, etc. Since they don't have any permanent dipole magnetic moment, so they don't show any rotational and vibrational motion. However, for heteronuclear spectra, they have different positive and negative center of point positive and negative uh, charge center, and that's why they show rotational and vibrational spectra. For example, HCl, NaCl, ZNS, etc. And if we talk about the Hamiltonian of heteronuclear molecules, then it will be H rotational plus H vibrational. So this is contribution of this is rotational contribution. This is vibrational contribution. Then as we solve problems, then we will go on discussing the rotational spectra, which has been covered in this week's lectures. So we will discuss that in more details once we start solving the problems related to that. Now let's start with the first problem of today's interaction session. The question says the lamp shift is option A caused by Thomas precision, option B a splitting between the 1s and 2s energy levels in hydrogen, C caused by vacuum fluctuations of the electromagnetic field, or option D none of the above. So I'll give you a few minutes to think about this question, and then we will discuss what will be the correct answer of this problem. So if we discuss about this question, so we had discussed a problem in the last introduction session. Uh, what was lamp shift? So basically, lamp shift is a difference between the energy difference between the two levels which have same value of n and j, but they differ in their energies. For example, if you talk about hydrogen levels, it was found that two levels, that is 2s half and 2p half, n is equal to 2 for both the levels and j equals to half. So and we know the energy depends upon the value of n. So since n is, and again if you talk about the arrangement of levels in case of ls coupling, then they are arranged in terms of j values. So here they have same n and same j values, however they differ in their energies, which is called as lamb shift. It was first experimentally observed by lamb and uh, it was first experimentally observed by Lamb and Rutherford. So the question says, what is the cause of those lamb shift? So the difference between the energy is given as, so if you see the energy difference delta E, it is 0.0353 centimeter inverse. So options are caused by Thomas precision. Option B, a splitting between 1s and 2s energy levels in hydrogen. It will be not correct because it is so seen between 2s and 2p. So it will be 2s and 2p caused by vacuum fluctuations of the electromagnetic field, and D, none of the above. So actually the correct option will be, it is caused by the vacuum fluctuations of electromagnetic field. Basically this Lamb shift is a phenomenon which arises in quantum electrodynamics, or QED, which was not discussed by theories that was given by like Dirac theory. So if we talk about the experimental verification, so there was beam of hydrogen, then there was a slit, it was passed through that slit, and then there was electromagnetic field applied, and then there was a charge collector. From that it was found that there is a deviation of from the predictions that was given by Dirac equation, and according to Dirac, it was predicted that these energy levels to be degenerate. That is, they should have same energy, but it was found that uh, they are not same in energy. There is some small energy difference between the two levels, and that is caused by the vacuum fluctuations of the electromagnetic field. So this is the correct option. That is option C. Now, question number two. Question number two says, what is the total magnetic moment of an atom in the state 3p0? And in bracket it is mentioned that do not consider the contribution due to the nucleus. So we need to only talk about the magnetic moment of the atom, that is in terms of Bohr magneton. That's why the options you see, the options are option A 0, option B 2 mu b, option C root 3 mu b, and option D root 6 mu b. So here all the options are in terms of mu b, and we know mu b or Bohr magneton is a unit of magnetic moment in atom, or atomic magnetic moment, magnetic dipole moment basically. So we need to find out the magnetic moment of an atom in the state 3p0. So I'll give you a few minutes to think about this question, and then we will discuss what will be the correct option. So if we discuss about this question, so we know the value of the expression for magnetic moment is given by the total magnetic moment. Total magnetic moment means mj, total magnetic moment, m corresponding to j, that is the total quantum number, and this is gj mu b j into j plus 1 root over. So it is according to the postulates of quantum mechanics. Now if we see the level, it is 3p0. For 3p0, 2s plus 1 is equals to 3. That implies s equals to 1. P means l equals to 1 and j is 0. So since j is 0, if you put the value of j here, so mj will be gj mu b j into j plus 1 root over, that implies gj mu b into 0, which is 0. So the correct answer will be option A, that is 0. But if you talk about some other levels, then in that case, what was the then also if you remember in the last interaction session we solved a problem, but there the j was not. For example, if you take 2s half, so if we want to calculate the value of magnetic total magnetic moment, then we need value of both we need value of all the quantum number, that is s, l and j. So here s is half because 2s plus 1 is 2 here, and then for s, l is 0 and j is half given here. So first, if you see the formula, it is mj gj mu b j into j plus 1 root over. So here since j is not equal to 0, so we first need to find out the value of gj. So gj is 1 plus j into j plus 1 minus l into l plus 1 plus s into s plus 1 divided by 2 j into j plus 1. So we need to first calculate the value of gj, and then if we put the value of gj in this expression, then we will get the value of the total magnetic moment. But here in this question, since it was clearly we can clearly see that j is equals to 0, and in the formula we need to put the value of j. So since j 0 means it is 0, but in some cases j is not equal to 0. Even if j is not equal to 0, there will be zero magnetic dipole moment, and that comes due to the gj value. When gj becomes 0, then magnetic dipole becomes 0. I hope this is clear to everyone. And then we will move to question number 3. Question number 3 says, which of the following molecule is a microwave active molecule? Options are uh, option A CO2, option B H2, option C HCl, and option D Cl2. So we had also discussed this concept in the beginning of our instruction session. I don't think there will be any problem. So after a few minutes, we will discuss what will be the correct option. So if we discuss about the microwave active molecule, so if you see, so at the beginning of today's discussion we were discussing about the types of molecule. The two types of molecule were homonuclear molecule and heteronuclear molecule, and the definition was those molecules which doesn't have any permanent dipole moment. They are homonuclear and they are not they don't show any rotational and vibrational spectra. However, for heteronuclear molecule, since they have permanent dipole moment, they show vibrational rotational spectra. And they show vibrational rotational spectra means they are microwave active, because we had also discussed the rotational spectra. So here we discussed the rotational spectra. If you see the order of the energy, then the rotational spectra lie lie in the microwave region of the electromagnetic spectrum. And the microwave region means it is very high frequency the order of gigahertz. Basically it is RF and microwave, starting from megahertz, and that goes up to gigahertz. Now if we see from the options, we need to find out which of the molecule out of these four molecules has permanent dipole moment. Now you see here in A, the option is CO2. How the CO2 is formed? It is like this. Here we know the dipole moment comes as a result of a difference in electronegativity between the two atoms. Now if you see the electronegativity of oxygen, the electronegativity of oxygen is greater than that of carbon. However, due to the linear structure, suppose there will be delta minus delta plus, then again here will be delta minus delta plus. Due to the linear structure, the effect gets cancelled out and there is a net zero polarity, or the molecule's polarity is overall zero. Linear structure that result in polarity equals to zero. So this is not correct. And if you talk about hydrogen, then they have same molecule, so there are no net dipole moment. And if you talk about chlorine also, since they are same molecule, chlorine and chlorine, they also don't have any permanent dipole moment. However, if you talk about HCl, the electronegativity of chlorine is greater than the electronegativity of hydrogen. So if you see, this is H and Cl, so there will be del plus, del minus, and due to that, if you see, this will be H and this will be Cl. So this will be center of positive charge, this will be center of negative charge, and since the center of positive charge and center of negative charge doesn't coincide with each other, there will be net magnetic dipole moment, and this results in the microactive nature of the molecule. So the correct option is option C, HCl. Now if we move to the fourth question, the question is, a magnetic field of 0.5 Tesla is applied on a sample of certain element. How far apart are the G-man components of wavelength 5000 Armstrong? Options are option A 0.0589 Armstrong, option B 0.135 Armstrong, option C 0.76 Armstrong, or option D 0.025 Armstrong. So this question is based on, since here this is magnetic field applied and we know the splitting of spectral line in presence of magnetic field is called as G-Man's effect. Also in the question it is given as G-Man components. So the same type of question we have already solved in previous interaction session. So it will not be that much difficult for you if you are following the interaction sessions regularly. So so I'll give you a few minutes to think about this question and try it, and then we'll discuss what will be the correct option. So if we if you remember in the last introduction session while discussing about G-man effect, so the difference in frequency of the energy levels due to the effect of the magnetic field was calculated, and that was nu equals to Eb by 4 pi m, or delta nu, or nu we can say nu or delta nu. So basically why this happens, we know due to the orbital and spin motion of electrons in an atom, they have dipole moment. One is the angular momentum, and then due to that they have dipole moment. And when the atom is placed in an external magnetic field, then there is interaction between the dipole atomic dipole moment and the magnetic field, due to which there is change in energy, and that energy gets reflected in terms of the splitting of energy levels. And due to the splitting, the due to those since the splitting occurs, then the due to a more number of levels, we get a number of spectral lines which was not present when the atom was then when there was no magnetic field. For example, there are two types of G-man effect. One was normal G-man effect, another was anomalous G-man effect. In case of normal G-man effect, it was found that the splitting occurs between the split one single spectral line splits into three different spectral lines. However, in case of anomalous Zeeman effect, it was found that it splits into more than three spectral lines which are unequally placed. So if you remember, this was the formula, and we know E is equals to h nu, or nu is c by lambda. So since nu is Eb by 4 pi m, this is not b, this is m, and here it says how far apart are the component of wavelength. So lambda is given to us, lambda is 5000 Armstrong, and we need to find out what is del lambda. So nu is Eb by 4 pi m, that implies c by lambda is equals to Eb by 4 pi m. So minus c by lambda square delta lambda will be Eb by 4 pi mc. So what will be the value of del lambda? So delta lambda will be E b lambda square divided by 4 pi mc. So this is the expression, and from this expression, if you put the values, E is 1.6 into 10 to the power minus 19 into B is 0.5 into lambda square is lambda is 5000 square into Armstrong 10 to the power minus 20 divided by 4 into 3.142 into mass of electron 9.1 into 10 to the power minus 31 into C 3 into 10 to the power 8 meter per second. So if you solve it, it will come out 0.0589 into 10 to the power minus 10 ampere into, sorry, 10 to the 10 to the minus 10 meter, or if you convert, it will be 0.0589 into 10 to the power minus 10, sorry, 10 to the minus 10 meter means Armstrong. It will be Armstrong. So the correct answer is 0.0589 Armstrong, which is option A, 0.0589 Armstrong. So delta nu minus L by lambda square delta lambda. I hope this is clear to everyone. Now let's move to question number 5. Question number 5 says, find the value of magnetic field required to observe the normal G-man effect if a spectrometer can resolve the spectral line separated by 0.5 Armstrong at 4000 Armstrong. So this question is pretty much similar to the previous question, but here we need to calculate what is the magnetic field, and the value of lambda is given to us. Lambda is 4000 Armstrong, and delta lambda, that is the resolution, is given 0.5 Armstrong. So you will use same formula and we will calculate the value of magnetic field. Options are option A 5.438 Tesla, option B 1.08 Tesla, option C 3.09 Tesla, option D 6.626 Tesla. So I'll give you a few minutes to think about this question and try it, and then we will discuss what will be the correct answer. So similarly to the previous question, it was delta nu was EB by 4 pi m, that means C by lambda square delta lambda was EB by 4 pi m. That implies B will be 4 pi mc delta lambda divided by lambda square E. So B will be equals to 4 into 3.142 into m 9.1 into 10 to the power minus 31 into C 3 into 10 to the power 8 into delta lambda. Delta lambda is given to us 0.5 Armstrong. So 0.5 into 10 to the power minus 10 divided by 1.6 into 10 to the power minus 19 into E square. It was E lambda square. So lambda was 4000 Armstrong. So 4000 square into 10 to the power minus 20. So if we solve it, it will be 4 pi into 27 roughly 9.1 into 3 into 0.5 divided by 1.6 into 1.6 10 to the power minus 41 plus 8 plus 10 plus 19. So it will come out to be 6.626 Tesla. So the correct option will be option D. So with this, so these two questions are pretty much similar and they were based on G-Mann's effect. Now if we discuss question number 6. Question number 6 says, how many spectroscopic terms result from the LS coupling of 3p electron and 3d electron? Options are option A 3, option B 6, option C 12, and option D 16. So this question is based on the concept of LS coupling. So in LS coupling, what happens? First, individual L, they are added vectorically to give us the total L. Then individual spin quantum numbers, they get algebraically added. They undergo vector addition to give us total spin capital S. Then the L and S, they give the value of J. So corresponding to the value of L, S, and J, there will be spectroscopic terms. So these are the four options. So after a few minutes, so I'll give you a few minutes to think about this question and try it. What will be the number of spectroscopic terms? So when there is coupling between LS coupling between 3p and 3p electron and 3d electron, and then we will discuss what will be the correct answer. So if we discuss now, this is 3p electron. For 3p electron, L1 will be 1, and since it is 1 electron, S1 will be half. Then for 3d electron, L2 will be 2, S2 will be half. So L will be L1 plus L2. We know it will be 1 plus 2, 2, 1 minus 2 mod. So it will be 3, 2, 1. Then S, similarly, S will be S1 plus S2, half plus half, half minus half. It will be 1 and 0. So now S is 0, L is 1, so J will be 1. S is 1, L is 1, J will be 0, 1, 2. S is 0, L is 2, J is 2. S is 1, L is 2, so J will be 1, 2, 3. Then S is 0, L is 3, J is 3, S0, sorry, S1, L3, J is 2, 3, 4. So, how many number of terms? So, S0, L1, J1. So, S0 means it is 2S plus 1 is 1. So, this will be 1P1. It will be 3P0, 1, 2. It will be 1D2. It will be 3D, 1, 2, 3. It will be 1F3. It will be 3F, 2, 3, 4. So this is one term, this is three term, this is one term, this is three term, this is one term, this is three term. So total there will be 12 terms, 12 spectroscopic terms. So if you if we discuss it once again, so the question was how many spectroscopic terms result from the LS coupling of 3p electron and 3d electron. So 3p electron L1 is 1 and for 3d electron L2 is 2. So if you add them vectorically, it will be 2 plus 1 and 2 minus 1. 2 plus 1 is 3, 2 minus 1 is 1. So with one increment between 2 and 3, it will be 1, 2, 3. Similarly for S, half, S1 is half, S2 is half. So S1 plus S2 will be half plus half and half minus half, 0 and 1. So there will be 6 combinations. Since there are 3 L values and 2 S values, there will be 6 there will be 6 combinations of L and S. So correspond to this. So since here S is equals to 1, 2S plus 1 is 3. So there will be triplet terms. So for 3S1 value, so there are 3 triplet terms, 3 into 3, 9. And then for 3S0 values, there are 3 singlet terms. So 9 plus 3, 12. So total number of spectroscopic terms coming out when the LS coupling occurs between one 3D electron and one 3P electron is 12. I hope this is clear to everyone. Now we will move to question number 7. Question number 7 says the masses of carbon and oxygen in carbon monoxide molecule are 1.99 into 10 to the power minus 26 kg and 2.66 into 10 to the power minus 26 kg respectively. Find the reduced mass of carbon monoxide molecule. Options are option A 3.32 into 10 to the minus 26 kg, option B 1.138 into 10 to the minus 26 kg, option C 2.325 into 10 to the minus 26 kg, and option D 4.65 into 10 to the minus 26 kg. So these are the four options, and we need to find out what is the reduced mass of the carbon monoxide molecule. So I request you to try this question and then we will discuss which will be the correct option. So if we discuss, we know the expression for reduced mass is m m1 m2 divided by m1 plus m2. If you put the values, it will be 1.99 into 2.66 divided by 1.99 plus 2.66 into 10 to the power minus 26. We can take it as common, so it will be 1.138 into 10 to the power minus 26 kg. So the correct answer is option B, 1.13 into 10 to the minus 26 kg. And now question number 8 says the number of permitted transitions from 2p3 by 2 to 2s half is, options are option A 3, option B 6, option C 9 and option D 10. So here we need to first split the levels according to their j values, because here 2p3 by 2 and 2s have here, so j has significance. So corresponding to the j values of the levels, there will be mj values, and then there will be splitting where the delta mj will, the selection rule will be there. Delta mj will be 0 plus minus 1 and delta j will be 0 when, so when j is equal to delta j is equal to 0, then delta j is equal to 0 is not allowed. So according to that transition rules, we will calculate what we will draw transitions, and then we will find out what are the possible number of transitions. So I'll give you a few minutes to think about this question, and then we'll discuss what will be the correct answer, what will be the current total number of transitions between these two levels. So if we about the question, then it was 2p 3 by 2. So j equals to 3 by 2. So what are the values of mj? Mj will be minus 3 by 2 minus half 3 by 2. Then for 2s half, j is half. So mj will be minus half and plus half. So 2p 3 by 2, there will be 4 levels. 2s half, there will be 2 levels. So 2p 3 by 2, 1 2 3 4. So this is minus 3 by 2 minus half 3 by 2, then 2s half minus half plus half. So what is the selection rule? Selection rule is delta mj is 0 plus minus 1, and when there are same j values, then there will be and j equal to 0 to j equal to 0 not allowed. So now from 3 by 2 transition will be from 3 by 2 to half, because 3 by 2 to half is 3 by 2 minus half, which is 1. So delta mj is 1. So for this delta mj is 1. Similarly delta mj will be 1 for half to minus half. So for these two delta mj is 1, then at delta mj is 0, then half to half minus half to minus half. For these two delta mj is 0, and then minus 3 by 2 to minus half, minus 3 by 2 to minus half, and minus half to plus half. These two delta mj will be minus 1. So there will be 1, 2, 3, 4, 5, 6. There will be 6 transitions. So the correct option is option B, that is 6. So now let's move to the question number 9. Question number 9 says the splitting of spectral lines in presence of electric field is known as option A. Option A is normal Zeeman effect. Option B is anomalous effect. Anomalous Zeeman effect. Option C is Stark effect, and option D is Pastenberg effect. So if you discover this question, we know in presence of magnetic field, the splitting of spectral line is called as Zeeman effect, and there is two types of Zeeman effect. One is normal Zeeman effect, another is anomalous Zeeman effect. So these two options are not correct. And if you talk about Pastenberg effect, what is Pastenberg effect? So when the magnetic field is too strong, then the coupling between L and S is broken. Then J has no significance in that case, because the L and S, they precess independently around B. So in that case, there will be that effect is called the Pastenberg effect. So the correct option is Stark effect. This is correct. So there are also two types of, one is linear Stark effect, then another is quadratic Stark effect. So I hope this is clear to you. So the correct option will be Stark effect. Now question number 10. Question number 10 says an atom having spin I equals to 3 have two levels, 2d 3 by 2 and 2d 2p half. Find the expected number of components in the hyperfine structure of the corresponding spectral line. Options are option A 2, option B 4, option C 6, and option D 9. So this question is related to hyperfine structure, and we know hyperfine structure comes due to the nuclear spin. So for nuclear spin, here is nuclear spin I is 3. So corresponding to I is 3, we will see what will be the correct option. So these are the four options. I'll give you a few minutes to think about this question, and then we will discuss what will be the correct option. So if we discuss it, we know in case of 2d 3 by 2 and 2p half. So for 2d 3 by 2, j is 3 by 2 and I is 3. So what will be f? F will be j plus I to j minus I mod. So j plus I is 9 by 2 and j minus I mod is 3 minus 3 by 2 will be 3 by 2. So there will be 7 by 2, 5 by 2. So there are 4 f values, and again for 2p half, j is half, I is 3. So f will be 3 plus half, 3 minus half. So 3 plus half is 7 by 2 and 5 by 2. So two values. So according to these f values, the label will be getting splitted. So 2d 3 by 2, it will split into 4 labels: 1, 2, 3, 4. So this is f equals to 3 by 2, 5 by 2, 7 by 2, 9 by 2. And then to p half, it will be splitted into 2 labels: 5 by 2 and 7 by 2. Now what is the selection rule? Similar, the selection rule is delta f is equal to 0 plus minus 1. So delta f is equals to 0 plus minus 1, and f0 to f0 is not allowed. So similar to the previous question, so 9 by 2 minus 7 by 2, 9 by 2 minus 7 by 2 is 1, then 7 by 2 minus 5 by 2 is 1. So they corresponds to delta f is equals to 1, and then correspond delta f 0 means 7 by 2 to 7 by 2, 5 by 2 to 5 by 2. So for these two, delta f is 0, and then for minus 1, it will be 5 by 2 to 7 by 2 and 3 by 2 to 5 by 2. So 5 by 2 to 7 by 2, 3 by 2 to 5 by 2. So here delta f is minus 1. So there are, so similarly to previous question, 1, 2, 3, 4, 5, 6. So there are 6 transitions that are allowed. So the correct option is option C, that is 6. So now we come to question number 11. Question number 11 says, for carbon monoxide molecule, let R is the bond length, I is moment of inertia, and M is the reduced mass. Then what will be the correct relation? Option A is R is equals to I by M root over. Option B, R is equals to 2I by M root over. Option C, R equals to I by 2M root over. Or option D, R equals to half I by M root over. So these are the 4 options, and we need to find out what is the correct one. So I'll give you a few minutes to discuss, and then we will I'll give you a few minutes to think about this question, and then we will discuss. So we know it is, if we talk about the expression for moment of inertia, so I is m r square, that implies r square will be I by m and r will be I by m root over. So the correct option will be option A. So we will discuss a few more problems now. Uh, so those problems that are based on rotational spectra. Okay, so question says the moment of inertia of carbon monoxide molecule is 1.46 into 10 minus 46 kg meter square. So moment of inertia for carbon dioxide molecule is 1.46 into 10 to the power minus 46 kg meter square. Now calculate the energy in EV and the angular velocity in the lowest rotational energy level of carbon monoxide. So we need to calculate the energy in electron volt and the angular velocity, and the angular velocity, that is omega, in the lowest rotational energy level, in the lowest rotational energy level. So given, this is the question, given h is 6.63 into 10 to the power minus 34 joule into second, and 1 electron volt is 1.6 into 10 to the power minus 19 joule, and we need to find out what is the energy of the lowest rotational level and what is the angular velocity. So what is the angular velocity and what is the energy? So I'll give you a few minutes to think about this question and calculate, and then we will discuss. So we know the expression for uh, energy of a rotating diatomic molecule is given by E is equals to h square by 8 pi square I j into j plus 1. So for lowest level j is 1, so j into j plus 1 is 2. Now E j equal to 1 will be h cross square by 4 pi square I. Now we know h cross h, the value of h square, h is 6.63 into 10 to the power minus 34 joule into second square divided by 4 into 3.14 square into I, moment of inertia was given in the question 1.46 into 10 to the power minus 46. So if you calculate it, it will come out to be 7.63 into 10 to the power minus 27 joule. So energy in electron volt will be 7.63 into 10 to the power minus 27 divided by 1.60 into 10 to the power minus 19. It will be 4.77 into 10 to the power minus 4 ev. So if you remember the rotational, we had discussed rotational level energy level, the order of rotational energy level is lesser as compared to electronic level, which are in terms of ev, but now here it is 10 to the minus 4 ev. So let me add another slide. So and we know T is given by I omega square, so omega will be 2e by I square root. That implies 2 into e is 7.63 into 10 to the power minus 23 divided by 1.46 into 10 to the power minus 46 root over. So if you calculate it, will give you 1.02 into 10 to the power 12 radian per second, which is the unit of angular, which is the unit of angular velocity. So the angular, so what are the answers? Energy in ev is 4.77 into 10 to the power minus 4 electron volt, and omega will be 1.02 into 10 to the power 12 radian per second. So these were a few questions that we discussed, and they were based on LS coupling, the concepts of LS coupling, uh, G-man effect, and the concepts of rotational spectra of molecule. So in rotational spectra also there are two types of case that must have been discussed. One is rigid rotator, another is non-rigid rotator. So I request everyone to follow the week lecture so that it will be better for your understanding to solve the problems. And I hope the problem that I have solved today, that will help you to solve the problem that you are being given in the assignments. So with this, I come to the end of today's interaction session. I would like to thank you all for joining in this course, and I wish you all the best for your upcoming course exam. That's it from my side today. So in the next week, we will meet at the same time, Monday 7 to 9 p.m. And in that session, we will discuss a few more questions that will be based on week 10 lectures, and that mainly covers the vibrational spectra of diatomic molecules. So till then, bye.